I've now got that heavy-duty 470K resistor between these high voltage capacitors. I put them in there, replaced that old one that was originally good but went bad during that capacitor work, so that one is out of the way. At this point, all of the remediation work has been completed except for the 100 ohm resistor. I will be putting the 100 ohm resistor in. It is a quite a robust resistor. As a matter of fact, this is a 5-watt resistor that I'm placing in the unit. It calls for a 2-watt. The way that this is going to be installed is such that it will be able to be removed, at least initially. I don't want to tack this in and waste a perfectly good resistor like this on nothing if I don't have to, until at least I could check some measurements. And then what I'm going to do, obviously, is I'm going to short across this resistor and see what the voltages are with the resistor out of play, compare it to these values on here, right? But the assumption is, of course, that the resistor will be the only way for electricity to carry across this pin over to here first. So we're going to go over here, remove that jump, and bring this resistor across that. I'm going to have to move this capacitor connection off pin 7 and place it down here with the others on pin 2, so I can remove that jump and bring the 100 ohm from there over to here. I put this on here originally because I had no plans on making this modification. It seemed like a likely place, but now that's going to have to go away. Of course, just in case there was any chance this might have all gone smoothly, pin 2 broke off. So I've decided to use, I believe this is pin 5. This is an unused pin on the schematic diagram, and I will be tying pin 7 to pin 5. As I look here, I don't see any placement on this pin. So 1 and obviously not 2, 3, 4, and then 5 is unused. Then we got 6, 7. So pin 5 it is. So I'm going to make a little elongation there, tie everything over. There it is. So here we have a pseudo-permanent fixture. We have pin 7 comes up 100 ohms back down to pin 5. Pin 5 is the new tie point for which everything feeds off of. And as we see here in the diagram, we see basically pin 7 to 100 ohms to where tie point where everything feeds off of. In our case, this point here is pin 5. So the 100 ohm modification or lack of modification or reintroduction is now back in place in this unit, and we are ready to fire things up. We're going to do a quick inspection. We're going to shake it out. We're going to make sure we don't have any solder blobs, shards of metal, and what have you. Clean up this table and start doing some power on testing. Also, what I really like to do, I think I totally missed this. I got to take out this bulb, make sure the bulb is good. Wow. Yeah, I forgot the bulb. Bulb's a type 47, ohms out okay. If it wasn't okay, I got a whole bunch of these brand new, so I could just pop one in. But this one appears okay, so we're going to go with this one, see if it lights up. If it doesn't, we'll throw a new one in. This is not a big deal. Another thing that I'm going to have to be aware of when I turn this thing on is how long it takes this surge resistor to make contact, or I'm going to have to bridge across this thing temporarily, because I'm going to be using a variac, and I can't really measure voltage if this thing is going to be cutting out a percentage of that voltage, because I'm going to need 100% of the voltage. What I really think I'm going to do is first see if this thing even works, measure this value here, see what I got resistance-wise, and then I'm going to temporarily take this out of circuit. I'm going to bridge this across before we start any variac testing. I think that's a safe way to go. It turns out that this is a 100 ohm resistor directly across the mains AC. The way this works is it's 100 ohms of resistance that drops the AC voltage until it heats up, and then an element, or somewhere there, yeah, there you go, an element closes, and then the resistance is gone, and then the voltage increases to full voltage, and it preserves the life of the components by doing so you don't get the full voltage when it turns on. So that's what that thing does. Again, not needed for the power on testing we're going to do. All of the tubes have been reintroduced into the unit at this point. I've decided to use a different method to turn up the unit. So they've been put back in, except for the CRT. I don't mind eating a tube or a rectifier tube in support of testing. It doesn't really bother me. I definitely can't afford eating a CRT over this. It's not going in. What I'm going to do is the power switch, which is here, being on position. I will set these knobs up according to the diagram for the voltage checking. There is a specific setting for all of these knobs, right? Power cord is fused. I'm going to leave the jumper in right now for this. I don't know what I'm going to do just yet. I'll make up my mind and add it to this video. Goes into my kilowatt meter that I just use as an ammeter or watt meter. This comes over to my Variac, which will be in the off position when we're ready to go. And that Variac in turn comes through and back to an isolation transformer, which is currently off. And that's a 1-to-1, but it actually brings it down to 117 volts. And I don't really use the voltage on here. I use the voltage on here. It gives me a pretty much accurate display of what I'm getting. I'm going to dial this up really slowly. And what I'm going to be looking for primarily is I'm going to tap off one of the heater voltages to look at the ratio of heater voltage to line voltage to make sure that we have fundamentally a good value for that, as well as a feed right off of that 100 ohm right there, which I can safely get to because of its position, as you see. So that's a good starting point right there. Because I do not have a tube on here, there are some good voltages that can be read off of the back of this too, such as the function of that rectifier right there. Should be just over 1,000 volts, as well as some other things we can get off the schematic diagram. According to the diagram, all switches will be in the counterclockwise position. Point of reference, the pin 7 portion of this 100 will be 430 volts at full power, full AC power. So that's something we'll also be checking off of the rectifier. The isolation transformer is now on. The Variac is now also on. There is no reference to ground in any part of this circuit whatsoever. So this is completely floating, this chassis right here. And I believe this to be the safest way to work on this type of equipment. There is no path to ground as long as your body is not touching ground. Mine is not. There's no way for any current to flow through you to ground. Also, the kilowatt generally turns on at just around 40 volts. You can see here at 43, it's just starting to turn on. Before that, there's not enough power to actually drive these things. It's just a note of reference. We could also see it around 48 volts, the start of a glow coming from the light bulb. This is also another good sign. The light bulb is starting to glow. I'll just bring that up. You can see at 50 volts, at 55 volts, the light bulb's getting brighter. So slowly bringing this thing up, I imagine that soon the heaters will start glowing and the tubes will record that as well. Even at these low voltages, there must be some sort of heating coming off these tubes, because we are starting to see some very low voltage rectification right here. You could see 31 volts coming off of there. I'm going to leave that clamped as we approach 60 volts and start to dial this up. It looks safe. There's no smoke, and we're going to turn it up even more. The thermistor has just clicked on, and we can see a rapid increase of voltage there on the rectifier. We're starting to see some glow in the tubes themselves, but at that moment right there, the thermistor, or the thermistor, whatever that's called, has just shorted itself out, right? And there's an appreciable climb, even though I have not increased the voltage of the Variac, still sitting at around 78. So the light has gotten brighter, everything's gotten brighter, and it's starting to turn up now. I'm going to bring it up to about 85. We're at about 78. We're going to come up to about 85 here, and we're going to see what that looks like. So 79, 80, 81, 82, 83, 84, and about 85 volts is now seeing 267. And though it can't be seen in the camera, the glow is now, you can now see the glow in a lot of the tubes, not just that one rectifier there, but it's becoming more apparent. So we've reached exactly 117 volts on the input, and on this 100 ohm resistor I'm seeing 413 volts DC, and it is showing on the diagram 430, right? It doesn't mean I'm on the correct side of the resistor, so I will unclamp this side of the resistor and come off onto the other side of the resistor, and I'll remove the and you can see it's just under 430 at 417. That's absolutely perfect. So I'm really happy with that. So this is obviously this side is obviously the side before it, the 100 ohms, and the 100 ohms is bringing it down effectively to 413. Now the question becomes, obviously, if we're expecting to see 430 volts, what happens if I crank this up to 123 volts? All right, so I'm going to bring this up to 123 now, which is my standard line voltage, right? And now we'll come back and we'll take a look and see what that looks like. We see 445, and we see 437. So that 100 ohm resistor does, and 123 is a bit high. I see about a 121 in my house. So 121 off the wall here that I just checked, and you see about 430. So what it does is it does take that 445 and it does bring it down to 430 volts, which is pretty good, which does align itself to the paperwork quite nicely, which does make a good argument for keeping it in there. So yeah, we could go with that. So now I've bumped it up to the actual line voltage in the house of 120 volts, about 121, what we see today. And what we want to see is the 430 volts that we're expecting, right? So we'll look at this resistor here a little before and after and see what gets us closer to the 430, to see if this resistor is a viable option to bring us closer to that voltage. Because from that 430, we're going to be breaking down all of the voltages for the DC rail right there. So let's see what we got, right? So the before, right, we're getting 438, which is in and of itself is not particularly bad. And we'll see what the 100 ohms will do, probably bring down a couple of volts, you know, nothing considerable. But we take a look at that right there, and it's almost spot on the money, 430, 428, right? So I don't think the 100 ohm resistor is a bad deal, especially since the voltage here can go up to, you know, 122. I've seen in the summer it can spike. It definitely couldn't hurt to keep that 100 ohm resistor in there, unless somebody can prove otherwise. I don't think it's quite terrible, you know. It's not a big deal. It's not hurting anyone. But I also took this movie purposely without the camera light on, so that we can see the tubes glowing, the silhouette. So you can see that right there. And I got, this one is not entirely very bright, but believe me, it's glowing from where I stand. And then we got these guys right here. And then there's this light. I could actually put this cap back on here because it actually glows green. Now I can power down the unit and go under the unit and check A, B, C, D. You know, I believe that they will be good, you know, based on stuff that we've already measured. But I still have to check this one out, this other rectifier, the IV2, expecting to see neg 1340. I do believe if I trace this one up and check this voltage drop here in this 100K resistor, then I could come off number 2 and see the neg 1180. That would be good enough for this test, right? And that could be found right off of here. And I'm definitely going to turn the camera back on with the light to do this. So we'll keep the voltages where they're at and make that measurement on the multimeter. The Fluke doesn't go this high, but the IM11 does. And the IM11 will tell you that the pin 3 that's supposed to be 1060 for the CRT on the IV2 tube after the reduction with the resistor is doing just that. So things are looking on the up and up as far as these voltages on that rectifier. So we're going to do some more tests up here to make sure all these voltages are good. I'm seeing that pin 6 and 7 are off on their measurements here. Pin 7 is reading 280 as expected. You can see it on my finger here. Pin 7 is reading 280. Pin 6 is reading 208. And it should be reading also 280. As I trace them back, and I checked before these resistors here because I was concerned because these are those resistors with the inductors wrapped around them, and you know, thankfully it is not that's causing it, so there's no cause for concern. So what I have to do here is really simple actually. I need to go back and check the pins 1 and the pin 6 coming off the 12BH7. I think that's what produces this this voltage. And if it turns out that the tube is so severely mismatched that there are two options. Number one is probably fixed by positionally, like probably this vertical position I believe here is adjusted to bring this back into balance. So I'm going to give that a shot, and I think that's what balances this out, and then that'll be fine. I won't worry about it any further. Or maybe the tube is weak. I have a feeling that this vertical position that does that. So we're going to test that out and see if that fixes that problem right there. So pin 7 is stationary. So pin 7 is stationary. The wraparound comes directly into the pin 1 of the 12BH7, right? There's no further modification, but pin 6 comes around, and the plate, as you can see, is pin 7 on 12BH7, goes through that 100 ohm resistor and is affected by the vertical position right here. So I've got the multimeter in pin 6 using the IM11 as support, and here we have it, the Fluke. Here's the pot for vertical position, and now all I have to do obviously is turn the pot, and we can see that we affect that voltage and balance out that those two signals right there. So if I turn it just right there, you can see that's 280, and I'm able to replicate that, right? I don't have to, but now I know that there's absolutely nothing wrong with that signal. I don't know why they would tell you to have them all in the counterclockwise most position and then give you the voltage for something that wouldn't apply. You know, you'd think that they would tell you that it was like, you know, 217 or something to that effect, but whatever. Okay, mystery is solved. A sufficient amount of testing has been done to tell me that the CRT will not explode if I plug it in. A lot of these voltages are sensitive to the fact that there is no load attached to them, right? So they're higher as expected than the diagram, but they are within the parameters that I would expect there to be for not having a CRT connected to it. Still not done yet, however. We know that now that rectifier is good. We know this rectifier is good. Still need to break out these here DC voltages. I still need to see them directly off of the capacitors that I put together under the unit, especially since they've been completely redone. And that'll give me some confidence because I know that all the breakaways for the DC voltages come off of those points there, right? So I got those 4, I got those 3, right? The 3 Gs, the A, B, C, D, and that should be pretty good because at that point I'll be pretty confident with, you see all these D4, D3, X, Y. Once I have those test points pretty much on point, I'll be happy with that, and then I at that point I could put the CRT in. So here are the measurements that have been taken at the electrolytic capacitors that have used this inline 100 ohm resistor. This guy throws a lot of heat. We've measured that everything is close enough within the parameters at that resistor. We saw the 430 was knocked out about 8 volts. That being said, the resistor is fine in or out at this point. Looking at this on the left side, we see that all of the voltage shows to be low. The 50 is negligible, doesn't matter. The voltage, all the voltages are low at 121.5 volts AC input. At the same time, the other capacitor shows the voltages, this capacitor right here, it shows the voltages to be somewhat high. So interesting. So what we're going to do, I've recorded the voltages AC because I'm going to pick this up tomorrow. And what I'm going to do very simply is I'm going to short across this resistor, effectively removing it from circuit. Allow this, I'm not even going to pick up the oscilloscope. I'm going to leave it just like this. Allow the oscilloscope to come to full temperature so we can bring it right back up to these parameters exactly like they are. And remeasure this again and see if it falls a couple of volts swinging in the other direction, you know, just the same, then we're going to remove this. If it swings, you know, entirely in an entirely different way, then we're going to keep it. So it's going to be non-destructive. It's simply going to be a small alligator jumper that's going to come across there, you know, something that's good enough for the current, you know, meet that, and that's it. And going to have these final values once and for all. I've got everything warming back up right now. As soon as it does, everything stabilizes. I'll come back to the Variac and make sure the voltage is set back to 121.5. Not worried about it right now. The reason why I have two sets of alligator clip jumpers here is because I'm not overly confident with these jumpers here. And I just wanted to make sure that I have, you know, since they're not very thick wire, you know, with the amount of wattage this is rated for, I just wanted to have two sets of jumpers. So that's why I did that. There's no other reason. And as soon as this heats up sufficiently, everything settles down, I'm going to take those readings and I'm going to put them in these blank areas of the papers so they could be analyzed again to determine if this resistor is actually needed. Looking at the numbers that I've gathered after looking at the bypass and without the bypass, it seems to me that the lower voltages closer to zero align themselves closer, obviously, than the higher voltages further than zero. So I decided at the end of the day, I'm going to leave that 100 ohm resistor in there and stay with these voltages and offsets rather than remove it, knowing that the voltage can climb yet another 2 volts on my power and further raise these up a couple of volts, right? Where this would further raise these even further a couple of volts further away from the specification. So it seems like the prudent choice is to stay with this. We're going to make that a permanent fixture and call it a day. So at this point, we can talk about putting the CRT back into the unit. I've taken the time to go around the outer portion of the bezel with some chrome polish and clean it up really nicely. You can see the contrast with the inner portion was, you know, quite dull, and now it has a nice shine to it. I wanted to get that done, obviously, before I put the bezel back in, before the CRT goes in. So this ring that you're looking at here runs around the entire outer portion of this metal piece. The bezel polished on the outside has now been reinstalled into the unit. You can see how the polishing turned out now. Nice and shiny, did clean up very well. I'm very happy with that. About 2 or 3 cleanings and 8,000 cigarettes later, the tube is returned to its former glory. So now it is ready to be put back into the unit. Now the CRT is installed and loosely mounted into the fixture. I don't know if the angle, you know, left or right on the CRT is straight yet. So obviously there's no need to tighten it down. Not that it's tightened very tightly at all. It's only supposed to be slightly secured with the rubber. But at this point, there's no need to do any of that. Only enough that the screws don't fall out the bottom, pretty much. And that it's seated correctly on the rubber and not metal to glass is pretty much the requirement at this point. Also, obviously, the back connector has been secured to the back of the CRT. So we're seeing some heater activity in the CRT, and for the very first time, we are actually seeing something coming up on the CRT itself. I want to point out that I just turned the knobs to get something to come up. It's not indicative of any actual reading, except for the fact that I've turned the spot in the back that you could see that it brings the spot in and out to something. This is not part of any calibration that I'm doing right now. You can see focus works. That it does bring into focus. The camera doesn't really do it justice because I guess I could get the camera to focus on that. And here's intensity. Does work. See there, horizontal position. So I can bring the line across. Right, I think I'll do that. Vertical position. Right, so that works, right? Horizontal gain. We could test that, right? Vertical gain, I don't think we're going to get vertical gain because we don't have an actual signal, right? Also frequency selector, well, it does work, you know. We are getting some function out of it. There's a nice slow, that's very interesting, look at that. That's line switch, so. Okay, so we got that, here's a frequency vernier. So that is working. We are definitely seeing something with that. Phase appears to have no function, obviously, without a signal. Vertical input. There's a response from the switch, but if I can't hook an input to it, I'm not going to see anything. External signal, external sync amplitude. We don't have an external sync, and then we have this sync selector. We're getting a response from it, but obviously don't have a function to it, right? So we are seeing functionality from the front. We're seeing functionality from this. Obviously, the true test of its initial functionality is going to be the calibration, right? That's the be-all and end-all of that, because through the calibration procedure is also some things where we're going to be testing off of some of these jacks and some of these jacks and running through the procedures in the book. I'm thinking that in and of itself is a different video. I think bringing us to this at this point here shows that the turn up and test of this oscilloscope is good. You know, a nice clean line, very sharp. You know, very sharp indeed. Considering I haven't really calibrated this, you know, I'm doing this eyeballing this, not using the procedure. You know, the oscilloscope is definitely coming to life. This is good. As if almost a twisted bit of irony, since we're still measuring voltages, I would be remiss if I did not measure the 1 volt AC sinusoidal peak-to-peak voltage coming off the test point of this unit. This is supposed to be a calibrated AC that's used for this oscilloscope, right? So having only one other working oscilloscope on hand, I've connected it to this oscilloscope. And indeed, we see a value of 60 hertz, which is obviously expected, 1.08 peak to peak, which is, you know, pretty good for this unit. Quite impressed. I shouldn't be too impressed though, because you know, I think it's just, you know, right off the coil. And I think if we kicked up the voltage over here, I think we would see that go up. As a matter of fact, we're going to do that. This is showing 108, and I'm at 118. I'm just going to bring that to 119.6. Yeah, and you can see it flutter up to 109. So, yeah, it's tied to the AC voltage. So, not overly impressive, but for what it is, because there's not a whole lot of circuitry there. It's not a regulated voltage, but okay, yeah, that works. So, that's good to know. And there's the external sync right there, which obviously it's just an input, so we're not going to worry about it. But I guess, you know, it's good to measure that as well, since it is a product of this. So there you go. There's the voltage measured for the 1 volt peak to peak from this unit.